Okay, now looking at June 2022, P23, for the first question, we have a solid metal sphere has a diameter of 3.42 plus minus 0.02 centimeter and a mass of 67 plus minus 2 grams. Calculate the density in gram per centimeter cube of the metal. So here the question specifically mentioned it that your density must be in gram per centimeter cube. So you actually don't need to bother changing your units to kg or to meter cube. All right, you can just leave the units as it is according to what the question has given you. So here, this one, if you want to find density, density is mass over volume, but mass is actually going to be 67. We already know that. Volume is the issue here because we do not have the volume given, but the diameter. So this one is mass over 4 over 3 pi r cube. But I think we better just change it to that diameter so that it's easier to see. This one will be 4 over 3 pi. Radius is usually half the diameter, so this one is d over 2 cube. We're actually going to get m over 1 over 3 pi d cube. Okay, so because, oh sorry, not pi d cube, this one should be 4 over 3 pi d cube over 8. Okay, my mistake. This one, the 4 will cancel, this one will give me 2. So this one should have been 6. Okay. So in terms of the diameter, it's actually 1 over 6 pi d cube rather than 4 over 3 pi r cube. So if we have the values here already, we can just easily sub in the values as 67 divided by 1 over 6 pi times with 3.42 cube. So our answer would be 1 over 6 times pi times 3.42 power 3, 67 divided by the answer. We should get the answer as 3.20 gram per centimeter cube. Okay, so this one should be the answer, 3.2 gram per centimeter cube. All right, so this is what we have. Now you can also easily just use it as pi r. You can also just use the equation as 4 over 3 pi r cube lah, if you wanted to find the final answer. In my case, I just have a preference to use back I just have a preference to use the equation according to what the equation has given me, because later on I need to calculate the uncertainty, percentage uncertainty, the density. So if I already express the equation in the form that the question has given me, this one will make my uncertainty calculation easier. Okay, so the next part of the question is asking you this actually, where they tell you, find out the percentage uncertainty in the density that you have calculated. So in the first place, I already found out my density equation as being similar to this. Let me just write it down. I found out that it is rho. Okay, maybe I should use a different color. I found out that the equation was rho equals to m over 1 over 6 pi d cube. So if I want percentage uncertainty, I just find the fractional uncertainty first. This one will tell me the fractional uncertainty of the density is equal to the fractional uncertainty of the mass plus 3 times the fractional uncertainty of my diameter. So from here, delta rho over rho will be 3.20 equals to delta m over m, which will be 2 over 67 plus with 3 divided by, plus with 3 times with 0.02 divided by 3.42. So eventually my delta rho is going to be 2 divided by 67 plus with 0.06 divided by 3.42 times with 3.20. So I'm going to get the answer is 0.15. Okay, so from here, I want to find the percentage uncertainty, right? So the percentage uncertainty would therefore be delta rho over rho times 100%, which would just be 0.15 times 100, giving me 1.5%. So this one should have been my answer. Hey, no, I got something else here. This one is 5. Okay, let me just check whether I did something wrong there. Oh, sorry, now I know why. This one actually should not have been put in. What I was finding was absolute uncertainty of the density. Okay, so there was actually no need to find the absolute uncertainty of the density. I just needed the expression in terms of fractional uncertainty, which was this. I should not have substituted 3.2 inside here. Okay, that was my mistake. So this one should have been just delta rho over rho 2 over 67 plus with 0.06 divided by 3.42. I'm going to get 0.047. Then from here, this one should have been 0.047 times 100, giving you 4.7%. Okay, so the answer is 4.7 here, according to what the marking scheme mentioned. It should be 4.7. At 2 SF, it will be 4.7. At 1 SF, it should be at 5%. Okay. All right, so there was a small mistake just now that I did. I actually found out absolute uncertainty instead. Okay, now there's another thing that I should probably mention to you. What if you use the equation as in the form of radius instead of diameter like I just did? If you had tried to use the form of equation in the form of radius instead of diameter, your expression, you need to be careful a bit. Okay, what do I mean by that is something like this. You see, if density, let me just write it as another separate working here. If this is density equals to m over 4 over, sorry, if this one is density equals to m over 4 over 3 pi r cubed, I can actually say that the fractional uncertainty of the density is equals to the fractional uncertainty of the mass plus 3 times the fractional uncertainty of r. Okay, here, because you use it as radius, but your question did not give you the values in terms of radius as well as its uncertainty, but instead they gave you in terms of diameter. There's this common mistake that people usually do. This one would be something like this. You see, if you wrote this, fractional uncertainty of density is equals to fractional uncertainty of the mass, 2 divided by 67 plus 3 times the fractional uncertainty of the radius. If I know that the diameter is 3.42, let me write it here. If I know that the diameter is 3.42 centimeter, the radius is half of my diameter. This one would mean 3.42 divided by 2, giving me 1.71 centimeter. Okay, so a lot of times people may have done it like this, where they found out the radius as half the diameter value that was given. You put here 1.71, but the thing that most people will make a mistake on is the uncertainty in the radius later on, because a lot of times they saw that diameter was plus minus was 3.42 centimeter plus minus 0.02 centimeter, They remember to divide they remember to get the radius value by dividing the diameter to give you this value, but somehow they forgot to do anything about the absolute uncertainty for the diameter. They just straight away use the absolute uncertainty for the diameter for the radius instead, where they put here 0.02. So if you do that, what you will eventually find out is that your answer is actually going to be different. You're going to get fractional uncertainty of your density as 0.06 divided by 1.71 plus with 2 divided by 67. You're going to get the answer as 0.065. The correct answer was that your fractional uncertainty should have been 0.047. But now you're getting 0.065. This is actually not correct. The one that is wrong here is this. You should not have used the absolute uncertainty for diameter for your radius. What you should have done was to also find the absolute uncertainty for your radius, meaning to say what you should do would be to find the absolute uncertainty of the radius too, which would be half the absolute uncertainty of your diameter. So this one should have been 0.02 divided by 2, giving you 0.01. So if you had done that, your fractional uncertainty would now be 2 divided by 67 plus 3 times with 0.01 divided by 1.71. You're going to get 0.047. So this is the same as what you have over here. Okay. So you could have used the equation in the form of radius too, but there's one thing that you needed to take note of. When you divide the diameter values to get the radius, you must also remember to divide your absolute uncertainty for the diameter. Okay, only then will you be getting the correct answer. All right, that's why just now I told you I have a tendency to always just change the equation to match whatever is given in the question. If the question gave me diameter, I will normally just change the equation such that it has diameter inside, so that later on I can just use the value straight away. Okay, so this one is for question 1. Then I will move on to the next one, question 2. Now for question 2, an archer releases an arrow towards a target at a velocity of 65 meters per second and the angle of 4.3 degrees above the horizontal as shown here. Okay, now when released, the tip of the arrow is a horizontal distance of 70 meters from the target and 1.66 meters above the horizontal ground. The arrow hits the center of the target. Now assume that air resistance is negligible and that all the mass of the arrow is at the tip. Okay, so this is what we are doing. There are a few significance here, few terms that are significant here. When they tell you air resistance is negligible, this one means only weight is acting. Only weight is acting on the arrow, therefore the acceleration is equals to g. Okay, and then here they tell you all the mass of the arrow is at the tip. The tip of the arrow is where your weight is at. Okay, so now they're asking you this particular thing in part A. Show that the time taken for the arrow to reach the target is 1.08 seconds. Right, so they give you quite a few information here. They want the time taken. So this one is something like projectile motion that gives you a parabolic curve. When you launch your arrow, it has a tendency to go like this. Okay, it follows a parabolic curve. Now, when you dealing with motion that is a parabolic curve, you normally need to analyze your motion in terms of horizontal and vertical motion. So this one, what are the things that you can do? You could have just analyzed your motion horizontally, because you see, they give you the horizontal distance, and they also kind of gave you the horizontal velocity, but you need to work it out. They already gave you the velocity with which your object was projected and the angle with which it was projected. So if I try to draw it out for you in a simple manner, this one is basically your object. Let's just consider it as a little point here. That is the velocity of 65 meters per second at an angle of 4.3 degrees above horizontal. So it went up and then it went all the way down. Okay, it's unlikely that at the point where it hits the target is actually at the same level as where it started. Okay, because you see here, if I try to draw this little line here, this would be where you started. This is where you started. But where you actually ended up hitting the target would probably be here, somewhere here. Okay, this one is your end point. Okay, you actually went below your starting point. All right. Okay, so back to this question here. Find out the time taken for the arrow to reach. Show that the time taken for the arrow to reach the target is 1.08 seconds. You can actually just calculate it out from considering the horizontal motion only. This one, what you can do is, remember, when it comes to projectile motion, we always mention this to you. Constant acceleration vertically, and then constant velocity horizontally. When you consider motion vertically, you're supposed to use the kinematics equation because you have constant acceleration here. But when you're talking about the case where you have, when you're talking about the horizontal motion part, you don't use your kinematics equation. Instead, you just use V is equals to S over T. That's what you're trying to use here. So if I tell you Vx is equals to Sx over T, your horizontal velocity, you can resolve it. This one, resolve vertically will be, maybe I just resolve it here first, sorry. Use a different color, red color. If I'm talking about the horizontal velocity, because the velocity is adjacent to the angle, this one will just be 65 cos 4.3. The vertical velocity, if I go and shift it here so that it completes the triangle, is opposite to my angle, so it will be a sine. So this one is actually 65 sine 4.3. Okay. So your horizontal velocity is this one, px. Okay. So you sub in your values. This one will be 65 cos 4.3 equals to 70 divided by t. T would therefore be 70 divided by 65 cos 4.3, giving you 1.08 seconds. Okay. So this one is you considering horizontal motion. Okay. We could probably find out the same thing by considering vertical motion also, but we don't have enough information to work with. We will actually have to do a lot more workings in order to find the same answer. So horizontal motion here is actually the most straightforward. Now, then the next thing would be part 2. Calculate the height of the center of the target above the ground. Okay. So in your case, the height of the center of the target above the ground is actually talking about this part. If this one is the center of the target where the arrow hit, they want the height above the ground. Now, if they want the height above the ground, this one you can actually do something like this. Remember just now I told you your arrow, when you fire it and as it hits the target, it will actually fall below your initial starting point. So let's just say that if you look at the diagram on the left, you manage to find out what is this displacement from the starting point. You can therefore find out what is the height, because you see, if I told you that your ground is, oh no, I actually deleted the diagram, sorry, let me just quickly redraw it for you. This one was 4.3, accidentally deleted, sorry. This one is, it was 4.3, sorry, this one is 6.65 meter per second. I fired it, it went up, and then it went all the way down. Okay, this one was my starting position just now. And then where I hit the target was here just now. Okay, this one is my target. So if you can find out the displacement here, you can actually find out where would be the height. Because just now, if you projected your target, your arrow like this here, like your arrow like this, okay, it hit here, they basically just want this height. Okay, if your starting position was basically here, maybe it's easier to show it from here. Okay, if you manage to find your displacement over here, you can find out the height, because you already know the total length as 1.66. See, this entire length is 1.66 meter. If you manage to find out how much is your displacement from the starting position, you minus it off from your total height, you can get the height above the ground. Okay, so that's what you want to do right here. So if this one was what you have just now, I tell you that this one is the ground, and this one is 1.66 meter. My height above the ground would just be 1.66 minus s. Maybe I just draw double arrows here. This one will just be 1.66 minus s. Okay, so your goal here is to find out what is s, your final displacement from your original starting point. Okay, so if you want to do this, you need to use your vertical motion. YH will be at the center of the target. YH will be at the center of the target. Because the question mentioned this, wait, no, let me just, they told you the arrow hits the center of the target, which is here. Then find out the height of the center of the target above the ground. Okay. Okay. So because of this statement here, they already mentioned now. Why must you find your height to the center of the target? Is because your arrow hit the center of the target here in the first place. Okay. Right. So back to this question. If you want to find out the displacement, or rather the position of the center of your target from your starting point, you use your kinematics equation, because you have to consider vertical motion here. So one of the things about kinematics equation was that you always have those four equations to use. B is equals to u plus at, s is equals to half u plus vt, s is equals to ut plus half at squared, and then v squared is equals to u squared plus 2as. Okay, So from here, sometimes when you want to determine which kinematic equations to use, it is often useful to list out certain variables. Now, if you consider the vertical motion, this one is for the vertical motion. Okay. I'm considering the vertical motion. Do you know the initial velocity? This one, you know the initial velocity as 65 sine 4.3. Because just now I actually did resolve the velocities out for you. This one was going to be 65 sine 4.3. This one is actually your vertical velocity, or uy lah, just to be consistent. This one is your initial vertical velocity. And then this one here, I also resolve it to give you 65 sine 4.3. This one was your Vx. Okay, so I already know the initial vertical velocity for the vertical motion. Do I know the final vertical velocity? This one is unknown. Do I know my time taken? I know the time taken is 1.08 seconds. This one I know. Because that time I mentioned to you one important thing about projectile motion. That one was this. I'm just going to write it somewhere at the top here. That time I mentioned time taken to move horizontally to a point is equals to time taken to move vertically to the same point. Okay, so if you look at the projectile motion case from here all the way to here, horizontally to move from the start to end position, it took you 1.08 seconds to move horizontally from the start to the end point here. Now your motion also has a vertical component to it. From the starting point to the end point here, you actually move vertically like this. This one will also take the same time as it took you to move horizontally to the same point. This one will also be 1.08 seconds. Okay. So that's why I can say that in terms of the vertical motion, the time is actually also 1.08 seconds. Because I already found out the time to move horizontally to the same point in the first place. So this one is 1.08 seconds. And then do I know my acceleration? My acceleration is going to be equal to gravitational acceleration. And then finally, the displacement is what I want to find. Now, usually when you list out your equations, or sorry, you list out your variables like this, you will notice that you often end up with two unknowns. In your case here, you actually have two unknowns, the final velocity and the displacement. So the key here is to always just to get rid of the unknown variable that you do not want. You see, the displacement is something that you do not know and is something you want to find out. Whereas the final velocity is something you do not know, but you do not even want to know what it is. So this is an unwanted variable. So when you want to choose your kinematics equations, which one to use, you generally just disregard the equations with the unwanted variable. So here, V is not what I want. I will just disregard any of the kinematics equation with V inside. So that would mean that the first equation is out, second equation is out, and then the fourth equation is out. So that would leave me with only the third equation, which is S equals to ut plus half at squared. I would need to use this to find my displacement. Okay. So from here, if I just write everything in, my initial motion is upwards. So upwards is considered to be positive for me. Okay, there's this sign convention last time that I mentioned to you guys. Which direction is assumed to be positive always follows your initial direction of motion. So since upwards is your initial direction of motion, upwards is considered to be positive. You get S equals to ut plus half AT square. Your initial vertical velocity would be 65 sine 4.3 times 1.08 plus with half times with negative 9.81, because your gravitational acceleration is opposite to your sign convention. 10 times 1.08. Your displacement now is therefore going to be, not forgetting there's a square here, sorry. So 65 sine 4.3 times 1.08. Then you have 0.5 times negative 9.81 times with 1.08 square. So that answer plus with this, you're going to get negative 0.46 meter. This is the final position of your object. It's actually negative 0.46 meter. So therefore, your height above ground would just be 1.66 minus 0.46. 1.66 minus 0.46, giving you 1.2 meter. Right? This one should be your answer, I hope. Yeah, 1.2 meter. Okay. Use S equals to UT plus half AT squared. That's where 1 mark comes from. Find out your final displacement at 0.46 meter. That's your other mark. And then height above ground is just finally 1.66 minus 0.46. Okay. So this is one question for kinematics. Right. So if this one is okay, then I'll move on to the next part. Okay. So this one, the next part is asking you this. By considering energy changes, state and explain how the final kinetic energy of the arrow as it hits the target compares with the initial kinetic energy immediately after release. A numerical calculation is not required. Okay. Wait now. Let me just get rid of this. Okay, here they just ask you to consider energy changes. State and explain how the final kinetic energy of the arrow as it hits the target compares to its initial kinetic energy immediately after release. Numerical calculation is not required. Okay, keyword here is you consider the energy changes only. Now, one thing to note was this. Last time I mentioned this to you guys before. If let's just say that this one was your ground, let me just draw an arrow here. This one was your ground. And then if you somehow projected your object with a certain speed, let's just say this one is 65 meters per second. And then this one was 65 cos 4.3. And then this one is 65 sine 4.3. We know that your object will travel like this in a parabolic curve. Now, at this point itself, when your object reach back the original starting point, your velocity vectors are same in magnitude, just that the direction is different. So what I mean by that is that if you're talking about the resultant velocity, this one will be 65 meters per second, tangent to the curve. And then your vertical velocity 6.5 sine 4.3. It will also be the same magnitude here, just that it's opposite in direction. This one will be 6.5 sine 4.3. Okay, let me just draw it here. This one will be 6.5 sine 4.3. Okay, 6.5 sine 4.3. And then this one would be 6.5 cos 4.3. Okay. So this one here, you will notice it was 65. This one will be 65. So the thing that you can actually draw here is that the KE, the conclusion you can draw here is that the KE here is the same as the start, because your velocity is the same as the starting point. Okay, now here your case here is that when we did the question, we already realized that your arrow will actually drop way below the starting point. It will actually drop even further, right? So if I try to look at the diagram here, my object will actually drop down even further like this, right over here. So what would you then say is that, if let's say that this is the point that you reach upon hitting your target, this point here would be more than 65 meter per second. This point here would definitely be more than 65 meter per second. Okay, your horizontal velocity will still be the same, no doubt, but your vertical velocity will not be the same anymore. It will actually be more than 6.5 sine 43, because your vertical velocity will tend to increase, right, from the maximum height. If this one was your maximum height, as you keep going down, your vertical velocity has a tendency to keep increasing. So here, at this point where you hit the target, you're definitely going to have a vertical velocity more than 6.5 sine 4.3, which in turn leads you to have a final speed or final velocity more than 65. So here, you would have therefore drawn a conclusion here that KE here is more than the start. Okay, here we would be able to say your KE here is more than the start, but the question doesn't want you to explain it in that way. The question actually wants you to explain it in terms of energy changes. They want you to explain it in terms of energy change. Okay, so energy change here would probably relate to you using conservation of energy. So here, what are the things that you can actually say about energy changes or conservation of energy? If you are going from here to here for maximum height, let me just draw a dividing line here. This is your dividing line here. If you were to move all the way down like this, what color? Orange, sorry. I use pink. You were to move all the way down here like this, your GPE is dropping, but your KE is increasing. So you kind of have to relate to this. GPE drop causes your KE to increase. So you want to relate it to your energy change. You could probably say something about going down, your GPE drop is actually larger than moving up. Therefore, your KE increase will be larger. Therefore, your final KE will be larger. Here they told you this, GPE has decreased. Total energy is conserved, therefore KE has increased. Okay, now if you look at this answer, it doesn't really make much sense to you, right? GPE has decreased, total energy conserved, so KE has increased. So if I wanted to write it, I'll probably write it like this now. GPE decrease is larger than the GPE decrease going down. GPE decrease going when the object goes down is larger than the GPE increase. It's larger than GPE increase when it went up. When it went up, okay? You just mentioned the fact that your GPE decrease going down is actually larger than your GPE increase when it went up, okay? So since energy is conserved, the KE increase going down will be larger. Therefore, final KE is larger. Okay, that's how I would word it now. I have to make use of the fact first, identifying that my GP decreased when the object went down is actually larger than when it went up. So since energy must be conserved here, meaning to say KE converted to GPE, sorry. Since energy is conserved here, this one refers to this fact where I told you that GPE is converted to KE and KE is converted to GPE. Since energy is conserved, the KE increase going down is going to be larger, will be larger. Therefore, final KE will be larger. Okay? This one will make much more sense than what you see in the marking scheme. Here they just say, oh, GPE decreased, so KE has increased. But it still doesn't tell you why the KE has increased to the point it's actually larger than your initial KE. Okay? So this one would be one way I would word the answer. Okay, so if this one is okay, then I move on to the next one. Okay. So this one should be okay. Okay, now this one is another one. Let me just clear off everything here. We move on to part 3. Question 3. Okay, now question 3. Define velocity. Velocity is just simply rate of change of velocity. This one is an easy one, mark, no issue here. Now for part B, they tell you you have a constant driving force of 2,400 Newton that acts on a car of mass 1,200 kg. The car accelerates from rest in a straight line along a horizontal road. Now assume that resistive forces acting on the car are negligible. So there are a few key words to see from here. Constant driving force, accelerating from rest, is a horizontal road, and no resistive forces. Okay, so see, these are some of the keywords to recognize here. So here, they ask you to calculate the acceleration of the car. This one is pretty straightforward. If you try to visualize what's happening here, let's just say that this one is your car that is 1,200 kg. Maybe I better draw the box bigger. If this one is your car, that is 1,200 kg. The only forces that are acting right now is actually just your constant driving force. So here, you have 2,400 Newton. This one is your driving force. Let's call this FD. Okay. So we do not have any friction or resistive forces to consider because the question already told you it's negligible. Okay, so no friction to consider. All right. Then from here, is there any other thing to consider, any other forces to consider? There isn't. Your motion, let's just assume it's going towards the right. All right. So the only forces that are acting is actually just your driving force of 2,400 Newton. Okay. Now, sometimes some students will say, shouldn't there be also weight as well as your normal reaction force and here on your diagram? Yes, that's correct. If you're just talking about the forces acting on the object, they're supposed to be the weight as well as your normal reaction force. But you see, because these forces are actually perpendicular to your motion, I don't really want to consider it. Because right now, when you're talking about your acceleration, this one is actually talking about acceleration in the direction of motion. So I only consider forces in the direction of motion. So the normal reaction force and the weight here, they're actually not in the direction of my motion at all. They don't contribute to my motion because they are perpendicular to it. So I don't consider this. All right, that's the reason why I normally do not draw it. Sometimes people will see why sometimes I draw it, sometimes I don't draw it. Okay, so here I don't want to really bother because they don't contribute to my motion. They don't contribute to my acceleration. So it's not considered. I only consider the forces that contributed to the motion or the acceleration. So in your case, this one is pretty straightforward. F net equals to MA. Your net force is actually just your driving force. It's 2,400 equals, sorry, your net force is 2,400. Your mass is 1,200 kg times A. So A is going to be 2.0 meter per second squared. Okay, pretty straightforward. Right, 2.0 meter per second squared. Okay, that one is okay. Then after that, if you were to just look at the other diagram, the other question, sorry. On figure 3.1, sketch a graph showing the variation with time of the velocity v of the car for the first 20 seconds of its motion. Okay, so this one, just sketch a graph showing the velocity v of the car. Right, so this one should be pretty straightforward. Just now, let me just rewrite this. F net equals to MA 2,400 equals to 1,200 A, where A is equals to 2.0 meter per second squared. Okay, so here they want you to sketch the variation of your velocity with time for the first 20 seconds of its motion. Okay, now this one kind of relates to your kinematics. If you look at the case on the left here, they told you that you have constant driving force, right? So you have constant driving force and then no air resistance, or rather no resistive forces. You have constant driving force, no resistive forces, no air resistance to consider. Therefore, F net is constant. Okay, because the only force now is just your driving force and it's supposed to be constant. The question already mentioned that there's no air resistance to consider also. So F net is constant. A is constant. The acceleration of 2 meters per second square here that you have is supposed to be constant throughout. Okay. And then after that, you have to draw on something that you learned from kinematics, where we told you last time the gradient of your VT graph is actually, maybe I reword this properly. Acceleration is rate of change of velocity. Is actually the gradient of your VT graph. Okay, so acceleration is gradient of your VT graph. From here, you can actually do something from there where you say this. If acceleration is constant, gradient must be constant. Okay, so you're supposed to draw a straight line graph. So it should be a straight line graph, but until where? So the question says that you started from rest. So therefore, you must start from the origin here. Now, the gradient that you draw must be in such a way that you're getting 2 meters per second square. If let's just say you draw it like this one would actually not be correct, because if let's just say I try to find the gradient here, this one is actually 50 divided by 20, giving me 2.5 meters per second. This is actually not correct. So how do I know which point should I use? So the easy way would be to do something like this, no? If let's just say I want to pick a convenient point 20 meter per second. I do it like this now. Since gradient should be 2 meter per second square, it will be my delta V over delta T equals to 2. So let's just say my T is 20. I consider 20 seconds. What should be my V then? This one will be delta V over 20 equals to 2. Delta V should be 40 meter per second. Not per second square, per second. Okay, so at 20 meter per second, my change in velocity should have been 40, but because I start from 0, the final velocity should be 40 lah. It should be this one. This one should be my final point. Okay, so this one should be my actual velocity. Sorry, this one should be the actual graph shape. Okay, there's a particular point you must pick. Okay, so just pick a convenient point. In my case, I pick 20 meter per second. So in my case, I pick 20 seconds as my point. So if gradient is 2 meter per second, delta V over delta T is 2. Time being 20 would mean that my change in velocity is 40 meter per second. So therefore, V is 40 meter per second. Since initial velocity is 0. Okay, so but let's double check your answer. They tell you straight line with origin with positive gradient label A and then ending at 2040. 2040 here is actually your coordinates. This one is your x-axis value 20 seconds. This is your y-axis value 40 meter per second. Okay, so this is for this. Then the next question will ask you to do is something else again with this question, with this diagram. They ask you to label this line A. Okay, so let's label this line A. Now, the next part of the question in the next page mentions this. In reality, resistive force due to air resistance actually acts on the car in B. Okay, so this is where they ask you to include resistive forces now. Resistive force due to air resistance acts on the car in B. This resistive force increases with speed until it becomes equal in magnitude to the driving force in a time of 12 seconds. Now, on figure 3.1, sketch a second line to show the variation with time till the velocity V of the car for the first 20 seconds of its motion, and then label this line B. Okay, so this one is with air resistance taken into account. The way they describe it here is in this manner. So this one is now a same object, 1280 kg. You again still have your driving force of 2400 Newton, but now you have resistive force. Let's call this R. Okay, so this R is proportional to speed, meaning to say if your V increase, your R increase. Okay, so if you look at this one is F net. Again, my motion is towards the right. Okay, F net is actually Ft minus R. Okay, but the thing here is that Ft, my driving force, is constant, but R has a tendency to increase because my speed will increase. You see, this one here is actually similar to terminal velocity. Similar to something similar to achieving terminal velocity. Okay. It is similar to achieving terminal velocity. Okay. It is akin to you achieving terminal velocity. The last time I always explained to you was an object that falls in the air, right? You have an object like this, and then after that I told you you have the weight W, and then you have air resistance, right? So your object is going down. This is your direction of acceleration. To put it simply, that time I mentioned to you, F net was equals to W minus D. F net with W minus R, sorry. I explained to you that time that F net is equals to W minus R. Okay. So what happened then was that your R increase, your F net decrease, so your A drops. Then after that, but V is still increasing, but at decreasing rate. Maybe I don't want to write the word but. This one is V is still increasing, but at decreasing rate. So then from there, what I then mentioned was that R continues to increase until it is equal to W. So from there, what you will say is that F net is equals to 0. Therefore, A is 0. Your object moves with constant velocity. Okay, this was basically how I explained your object achieving terminal velocity last time under kinematics. Okay, hopefully you remember some of the bits and pieces of the explanation. I omitted out certain explanations. I just told you the important things here. Okay, so when you had to take into account air resistance that time, as your object falls, your object actually starts to move, it actually speeds up. Your air resistance will increase, causing your net force to drop, and then your acceleration will drop. But even though your acceleration has dropped, it doesn't mean your object is slowing down. You're actually still speeding up. Your speed is still increasing, just that it is at a decreasing rate. Okay, so but because you're still speeding up, your R will actually still continue to increase, also at decreasing rate. So it continues to increase until it's equals to your weight. So at that point in time, your net force will be 0, your acceleration would be 0. Okay, this one is 0 acceleration. So your object will therefore moving with constant velocity, known as your terminal velocity. No? So it's kind of similar for your case right now. When you're talking about the object that is moving on the ground, you have driving force, which is constant, just like your weight last time. This one, the weight was supposed to be constant. And then you have a resistive force that increases with speed. Also same like the case last time when you're talking about terminal velocity, this one, the resistive force increases with time. So the case here is very similar. It's exactly the same, just that the context is different. It's for something moving on the ground right now. Your object will eventually achieve terminal velocity. So here, what I could probably say is this. This one, I will write it in detail for you now. Okay, so this one, number one, there is F net. Therefore, there is acceleration and hence speed increase. Okay, Ft minus R will tell you there's net force. There is acceleration. Wait, sorry. There is acceleration and hence speed increase. Okay, but here then I'll tell you that R is proportional to V. Therefore, R increase. So from here, F net drops, acceleration drops, object, or rather the car still speeds up, but at decreasing rate. Okay, this one, car still speeds up, but at decreasing rate. Okay, it will still speed up, but at decreasing rate. Okay, then this one, number 3, will be this one. So number 3 would be this part where I mentioned this. R increases, continues increasing until it's equals to W. Sorry, R continues increasing until it's equals to FD. Continues increasing until it is equal to FD. So from here is where your object moves with constant velocity. So let me get rid of some of the writings here. So your R continues increasing until it's equals to FD. Then after that, what will happen is that F net is 0, acceleration is 0, F net is 0, acceleration is 0. Therefore, car moves with constant speed. Okay, so that is actually what's happening here. Okay, they ask you to draw your graph to represent the motion of the graph, the motion of the object. Then, so the part where they told you that your drag force or resistive force increases until it's equals to your driving force, that one is at 12 seconds. The question already mentioned to you. The resistive force increases with speed until it becomes equal in magnitude to your driving force at 12 seconds. That means this one is at t equals to 12 seconds. You start moving with constant speed from 12 seconds onwards. Okay, so this part here is before 12 seconds. All right, so you want to draw your graph, I make use of the same thing. This one I'll probably need to draw it using a separate color. Let's just say I use a blue colored line. Now 12 seconds is here. All right, so 12 seconds is here. You already know you start to move with constant velocity at 12 seconds. So this one is one part of your line. The general shape is this now. Let me just try and draw it out for you. The general shape of your graph in terms of your velocity time should have been like this, where this one was 12 seconds. This one is you reaching your terminal velocity. Okay, so the thing is that if I draw it like this one seems very easy to draw, but this graph is actually wrong, especially this part here, because this one here is saying that my car move faster with resistive force than without. Okay, the original red line was this one, right? This one was without air resistance. So if I try to draw the line again, the blue colored line, and then the first portion I draw it higher than the original one, this one actually doesn't make sense because it will be telling me that my car was moving faster with resistive force than without. It should have been moving slower than without resistive force. So this one here, if I try to draw it like this using green, like this one is wrong. I drew it here like this just now, right? This one is actually also not correct. If I wanted to draw it correctly, it should have been like this. Oh, this one is the correct one. Okay. Let me just draw the pink color line. I'm going to use a different color Yeah, okay, it's better to use black. Black is easier to see. 12 seconds is where you reach constant speed, right? You just draw a line like this. Okay, make sure your speed becomes constant at 12 seconds. Okay, so this one is actually your correct line, the black color one that I just labeled for you here. All right. Don't draw the green colored line. Don't draw the blue colored line. That is not the correct way to draw your line. Cannot draw the green colored line because your object is not supposed to move faster with resistive force than without. You cannot draw the blue colored line also because of a similar reasoning. Because all this while you have been moving slow, your speed increase is getting lower and lower and lower. You are not gonna straight away start from this point. Okay, because you start from this point, this is considering that your speed actually was increasing constantly. Your acceleration was constant. So you start from this point, drawing the blue line, that's also wrong. It actually should be starting much lower because your speed was increasing less and less each time. So it should be the black colored line. The black colored line is actually the correct line to draw. Okay, right? Yeah, this question has quite a lot of things to take into account. Right, so if you just look at the wordings in the marking scheme, they just say line starting from origin with the same gradient. Okay, line starting at origin with the same gradient as A and beneath A at all points, and then the gradient is decreasing to 0, and then you have a straight horizontal line at 12 seconds and then ending at 20 seconds. And label this line B. Okay, so it's basically this black colored line right over here. So this line is B. Okay, right. Okay, just now I told you the green color line is wrong because the car moved faster. I'm just going to rewrite it properly. The car moved faster with air resistance, with resistive force than without. This one is actually wrong. Okay, let me just write it. This one is actually wrong. And then for the blue colored line, why was the blue colored line wrong? Is because of this. So again, let me just use red. Why the blue colored line is wrong? It's because the car immediately move at constant velocity after having speed increasing constantly. So it's saying car immediately move at constant speed after speed was increasing. Car immediately move at constant speed. Car immediately move at constant speed after speed was increasing uniformly or constantly. Okay, so B is wrong because it's saying to you that the car immediately moved at constant speed after speed was increasing uniformly. Okay, so this is wrong. We know that the speed must be increasing at decreasing rate. So if the speed was increasing at a decreasing rate, where your speed was constant after that, it should have been much lower, indicated by the black line there. All right. Okay, so this one is okay. Then after that, I move on to the next one, the last part here. Okay, now the last part here is basically just asking you this. At the time of t equals to 20 seconds, the driving force is now increased to 3,000 newtons and remain constant at this value. Describe how the velocity of the car changes due to the increase in this driving force. Okay, so after 20 seconds, you increase your driving force to 3,000 newton. Before this, it was 2,400 newton. But now they increase it to 3,000 Newton and they make it constant. How would the velocity of the car change due to the increase in your driving force? So here, if you look at it this way, on the right-hand side of your diagram, rather than having 2,400 Newton now after 20 seconds, you now have 3,000 Newton, okay? So you still have your resistive force here. What will now happen to the velocity of your car due to the increase in your driving force? Now, here, what will you say is that before 20 seconds, not at the 20-second mark, let's just say now, when t is equals to 20 seconds, your ft was equals to w. Sorry, ft not is equals. Ft is not equals to w. Your ft was equals to r. This one no f net, no acceleration. Okay. Then what happens then is you increase your driving force after 20 seconds would be this now. You're going to suddenly have a net force. So here you can just say that after 20 seconds, after t is equals to 20 seconds, your ft is more than your driving force is more than your resistive force. So there is f net and acceleration. Therefore, car speeds up. It accelerates. Okay, car speeds up or it accelerates. But then after that, since r still increases with speed, still increase with velocity or speed, eventually the car reaches a new terminal velocity, which is higher than before. Okay, you will now reach a new terminal velocity, which is higher than before. Okay, so initially after t goes to 20 seconds, your driving force is actually now more than your resistive force. You have net force, you have acceleration. The car will speed up, you will accelerate. But because at the same time your air resistance is still there and it still increases with speed, your car will eventually reach a new terminal velocity. Its speed will now also still continue increasing with decreasing rate. So it will eventually increase to the point is equal to the driving force again. So then it moves again with constant speed, but this time your constant speed is actually higher. Okay, so the way the marking scheme wrote it was something like this. Let me just erase everything. Okay, let me just say, and maybe not don't erase first. The question basically mentioned this now. They give you two variations of the answer, where they first told you the velocity or speed will increase to a new terminal speed, to a new constant speed, to a new maximum velocity or maximum speed, any one of this. Okay, the first one they say is the speed will now increase, but to a new terminal velocity or some other terms similar to it. Or you could also say something else. The car has acceleration right now because driving force is more than your resistive force. It will now go to a new higher terminal velocity, constant speed, or maximum velocity, maximum speed. Okay, it's basically the same thing lah. Just that they go and worded it bits and pieces, unlike what I just wrote at the top right hand corner. All right, you initially speed up, but eventually you will reach terminal velocity again. That's the better wording for it lah. It will initially speed up because the driving force is more than your resistive force, but because the resistive force increases with speed, your object reaches terminal velocity again, which is a higher value than before. Okay, right. So this one is okay, hopefully. So let me just clear this thing off. Yeah, when it comes to terminal velocity questions, it is usually very time consuming to explain it in detail. That's what I noticed. Okay, so this one is all right. Part question 3 is all right. Okay, then we go on to question 4. Okay, let's have a look at question 4. Okay, this one is derivation of your GPE, derivation of your energy. A mass M moves a vertical distance delta H in a uniform gravitational field and gains gravitational potential energy delta EP. The acceleration of free fall is G. Use concept of work done to show that delta EP is actually mg delta H. So make use of the concept of work done. Okay, this one is talking about the derivation of your change in GPE. So that time I think I did mention to you, let's just assume that you have an object at rest. This one is 0 meter per second. And it's on level ground like this. Okay, so you move it up a certain distance, dot, 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 like this. Say you move it up a certain distance, say delta H, like this. You move it out a distance of delta H with constant velocity. Okay, now this one I don't think I should write it with 0 meter per second because it doesn't make sense if I say constant velocity. So let's just say you have an object on the ground here, you move it up with constant velocity. You gave it an initial speed in the first place, let's just say that. Okay, you move it up with a certain velocity rather than from rest, but you make sure that you move it up with constant velocity. Okay, so you move it out a distance of H. If you want to make use of the concept of work done, this one, work done, remember, was W is equals to FD, right? Force and is the work done is the product of force and the distance moved in the direction of the force. So in your case here, that time we mentioned to you that F must be constant force and it must be an applied force and it must be in direction of motion. There was a condition to use W is equals to force times distance moved. So that one was that the force must be constant, it must be an applied force, not resultant force, and the force must be in the direction of motion. Okay, so in your case, if you want to apply it to your mass that's being moved upward as constant velocity, now you consider this, your object actually had weight W. Okay, maybe I should use a different color. Your object actually had weight W in the first place. Okay, it had weight W in the first place. Let's just call this weight W. Now to move it up at constant velocity, that would mean that your force applied must be equals to your weight. So here, let's just call this F here as your force applied. This one is your force applied. So your F at constant velocity, when you move your object up at constant velocity, F must be equals to W here. So it will automatically satisfy this already because the weight remains constant and you are moving at constant velocity, is your applied force will be a constant force. It's also an applied force in itself and it's in the direction of your motion. Okay, so from there you can now use W is equals to FD. This one would be okay now. This one I think is a bit misleading because weight is also W. This one I should have probably written it as work done. Okay. So your force applied is actually your weight W. Your distance moved is actually delta H. So this one will in turn become mg delta H. Okay. Work done is actually mg delta H. So there will be probably a statement that you would have to write. Work done is used to change the GPE. Therefore, work done is equals to the change in GPE, change Like in my case, I better just rewrite it according to your variables listed in the question. Rather than saying delta GPA, I better just write it as delta EP. Okay. So work done is used to change the GPE, therefore work done is delta EP. So delta EP is equals to mg delta H. This is how I would write the answer now. But let's just see how your marking scheme worded it. So they say work done is force times displacement. The force is mg and the distance is delta H. So work done is mg delta H and work is delta EP. So you get this, no? Okay. This one is derivation worth 2 marks. W is force times the work done is force times displacement, which you have right over here. Force is mg and distance is delta H, where you have in the second line here. And then work done is equals to change in GPE, or work done is equals to mg delta H, and work done is delta EP. It's basically the last two statements now. Okay. Yeah, you see the part where they told you this, and work done is this. It's actually referring to this statement here. Work done is used to change the GPE. Okay, you see they must have this. Work done is equals to mg delta H is actually this one here. But then after that, you had to write some sort of connecting statement to say that whatever work you do is actually used to change the GPE. That's why you see the word and here. So you must have this one. Okay. Only then can you then say work done is delta EP. Delta EP is mg delta H, no? Right? That's how the marking scheme worded it. No? Okay, so if this one is okay, then after that, I'll move on to the next part. Now, for part P, they tell you this. 0.6 kg mass is attached to a string which is wrapped around the wheel of a generator as shown. The mass is held stationary above the floor. When released, the mass initially accelerates and then falls at a steady speed and spins the wheel. The generator causes a current in the resistor. Air resistance is assumed negligible here. State the mean energy change when the mass is falling at steady speed. Okay, so maybe it'll be better to view it from the side. Let's just assume that this is the front view. Again, let's just say that this is the front view. If I were to try and see it from the side view, this one will be probably my wheel. And then this one is probably my string with the mass. Okay. So what you understood was that this one, let's just say side view. Right there. Oh, this one is the side view. So what you understand was that your object will actually fall downwards. Your direction of motion is downwards, but this one is moving with constant speed. Okay, it fell down with constant speed. And then another thing here that they mention is no air resistance. So the mean energy change when the mass is falling at steady speed. Now, under most circumstances, when you're talking about a falling mass like this, you would have probably said that the loss in GPE is equals to the gain in KE plus work done against friction. But because you see you have a generator here, you will probably say this one has electrical energy, no? Increase in electrical energy, right? Under most circumstances, if you try to see how the energy changes are occurring here for the falling mass, whatever loss in GPE that you have could be converted to gain in KE, could be converted to work done against friction, could be converted to gain in electrical energy. So here there are a few things that will actually tell you some of these are actually not applicable. So if you have constant speed, change in KE is actually 0. So this one is out. Okay. Then after that, is there any other thing that needs to be changed here? There's actually no other things to mention here. Your energy changes is mainly GPE, work done against friction, and electrical energy. So let's just see what the marking scheme says. You have gravitational potential energy as well as work done against friction. But here they call it to all. They didn't say what was the forms of energy change. They say the mean energy change when the mass is falling at a steady speed. Okay, meaning to say is talking about this GPE to friction. Okay. So state the mean energy change when the mass is falling at a steady speed. I think the emphasis is on this. Why did it fall at steady speed? What caused it? So you could probably just say that your GPE is converted to thermal energy. Now, because the wording is energy here, you cannot say work done against friction energy. You can probably just say as heat energy. Okay, the marking scheme put it as this now. Gravitational potential energy to thermal energy. Okay, this one you can just write it as gravitational potential energy to thermal energy. Okay, so what I can probably say here is this. The majority, if you do, maybe I don't like this now. Work done against friction. Why do I say work done against friction is actually the same as thermal heat energy? Work done against friction is dissipated as heat or thermal energy. You can probably understand work done against friction as this now. Okay, so your GPE loss is converted to work done against friction, but here you do not have work done against friction. You have some things here already stated as energy. You can probably just say as thermal energy, no? Because work done against friction is also dissipated as heat or thermal energy. Okay. So state the mean energy change when the work is falling at a steady, when the mass is falling at a steady rate. Okay. Now, some people may ask, why didn't I mention this also? Okay, now, if you're wondering why didn't I mention the loss in GP is converted to electrical energy, since the energy equation I wrote here is this, the way I would explain it would be probably that the question is asking you about the mass. The loss in GP is for the mass. The gain in KE is for the mass. The work done against friction is for the mass. But the electrical energy is not the mass that gain electrical energy. It's actually the generator that gain electrical energy. So for the part here where they say the mean energy change for the mass at steady speed, it will strictly be just these two. I won't mention electrical energy because it's not for the mass. It's for the generator. Okay. Right. So that one is okay. Then let me just go to the next part. Now, when falling at steady speed, the mass in B falls through a vertical distance of 1.4 meter a distance of, when falling a steady speed, the mass in B falls through a vertical distance of 1.4 meter in a time of 4 seconds. This causes a current of 90 milliamps in the resistor. The resistance of the resistor is 47 ohm. Calculate the rate of work done by the falling mass. Okay. So what is the rate of work done by the falling mass? Knowing this one, because the word did it as rate, this one must be per unit time. Okay. So the rate of work done by the falling mass, you can probably just say that P is actually change in GPE. The rate of work done by the falling mass is probably change in GPE divided by your time. So this one is mg delta h divided by time. This one will be, did they give you your mass? Yes, they give you 0.6. This one will be 0.6 times 9.81 times a distance of 1.4 divided by time of 4 seconds. You will get 0.6 times 9.81 times 1.4 divided by 4. You should get it as 2.06 watts. Your marking scheme would probably put it as 2.1 watts. Yeah. Okay. So they told you that this one is mg delta h divided by t. So just put in the values, you eventually get the power as 2.1 watts. All right. Then they ask you to find out the power dissipated in the resistor itself. So this one, you have value for current, you have value for resistance. This one immediately what should come to your mind is P is equals to I square R. So in my case, you just be 90 times 10 power minus 3, square the answer, square the value, sorry, then times with 47. 90 times 10 power minus 3 square times 47, you get 0.38 watts or 0.381 watts now if you want to round it up to 3SF. This one would be 0.381. Okay, so this one is 0.381. Marking scheme would again put it as 2SF, so it's 0.38 watts. Okay. Then efficiency of your generator. Efficiency of your generator, this one you should know it as efficiency being output power over input power. Wait, let me write it using a different color, green. Efficiency is output over input. Okay. Output power over input power. What is your output power? Your output power is your power dissipated by resistor. Your input power is actually the loss in your GPE. Power loss due to GPE. Oh, no. Rate of GPE loss. Because I'm talking about per unit time here. Power is per unit time, okay? That's why I worded it as rate of GPE loss. Okay. You can also see from the energy equation on the left-hand side here, this is really your input power. Okay. This is your P in. Your electrical energy is your P out. The other two here is kind of like your non-useful power. This is non-useful power or power loss. Okay. So it's P out to P in. So in your case, you just write it as 0.381 divided by 2.06. You're going to get the answer is 0.185. So this is your answer. Marking scheme would put it as 2SF is 0.18. Okay, it must be due to the fact that I use 3SF for my workings. That's why my answer is a bit different from your marking scheme. Because you see your marking scheme uses 2SF, 0.38 over 2.1, then you got 0.18. But I use 3SF, 0.381 divided by 2.06, so I got 0.185. If I rounded it up to 2SF, I will get 0.19. So it's seemingly different than what the marking scheme gave, right? But actually that one is of no consequence. Usually if the examiner sees that there's a very small difference here, they will see what is actually the value that you substituted. If the reason why the difference is there is because of the larger number of SF that you use in your calculation, then it's actually not an issue. They will just accept it as it is. It is actually a correct working in the first place. Okay, so this one is for energy, and this one is worth 9 marks. Okay, so next one should be on waves already, if I'm not mistaken. Okay, now this one is something quite different. Let me just clear off everything here. Now this one, question number 5. Parallel light rays from the sun are incident normally on a magnifying glass. The magnifying glass directs light to an area A of radius R as shown. The magnifying glass is circular in cross-section with a radius of 5.5 centimeter, and the intensity of the light from the sun incident on the magnifying glass is 1.3 kilowatts per meter square. Now, assume all the light incident on the magnifying glass is transmitted through it. Okay, so meaning to say no energy lost. In other words, they say all the light incident on the magnifying glass is transmitted through it. That means no energy loss. No energy loss through the glass. Okay. So from here, calculate the power of the light from the sun incident on the magnifying glass. So this one actually kind of makes use of your definition of intensity. Power of light from the sun incident on the magnifying glass. The intensity of light on the magnifying glass was already given to you as 1.3 kilowatts per meter square. So if you recall from the notes, intensity is actually either two definitions. Last time I told you is energy per unit time per unit area, right? But if let's just say you group these two together, if you group energy over time together, this one is actually power, right? So you could have actually said that intensity is actually power per unit area. So I'm making use of the second definition here. So this one is power over area. Intensity is 1.3 kilowatts times 10 power 3 equals to power over area. Area is already given to you. They told you it's a radius of 5.5 centimeter, right? So let me just write this out. Area of a circular cross section is pi r square. Okay, they give you radius. This is a circular magnifying glass. Okay, so this one would be pi times 5.5 times 10 power minus 2 squared. So power would thus be 5.5 times 10 power minus 2. Create the answer times pi times with 1.3 times 10 power 3. You should be getting 12.4 watts. Okay, hopefully I'm correct. Yes, your answer is 12.4 watts. At 2SF is 12 watts. Okay, So this one is okay. Now then the value of R of your radius is 1.5 millimeter. Calculate the intensity of the light on area A. Okay, this R that they're mentioning to you now is actually this R of the smaller area. They told you parallel from sun is the nominal magnifying glass. The magnifying glass directs to a light of area A and radius R. This one is not a magnifying glass, it's just some area with a radius and an area. Okay, so this R is talking about that little part there, this part here. Okay, so they want you to find out the intensity of the light on area A. Now, they already mentioned to you in the first place, assume that all light incident on the magnifying glass is transmitted through it. So what this means is that if you had a power of 12.4 watts through your magnifying glass, let's just say that this is your power in, you would have the same power out from the magnifying glass. Your power out would also be 12.4 watts. That's what the statement is supposed to mean to you. Okay, so that 12.4 watts of light energy will now be incident on this smaller area. So they want the new intensity. So this one is pretty straightforward. Intensity is again P over I R square. Your power is 12.4 divided by a smaller radius, pi times 1.5 times 10 power minus 3 square, giving you 1.5 times 10 power 3 square times, 1.5 times 10 power 3 square, the answer times with pi. 12.4 divided by the answer, you're going to get the answer as 1.75 times 10 power 6 watts per meter square. Sorry, 1.75 times 10 power 6 watts per meter square. Is this the answer? Yeah, you're going to get the answer as 1.7 times 10 power 6 watts per meter square. Again, they round it up to 2SF. Okay, so this one, no issue. Okay, then next one. Well, there's actually some other parts to this. Okay. Okay, now then from there, they tell you a laser emits a beam of electromagnetic waves of frequency 3.7 times 10 power 15 hertz in a vacuum. Show that the wavelength of the waves is 8.1 times 10 power minus 8 meter. And this one should be pretty straightforward. Keyword here is electromagnetic waves. The moment you see the term electromagnetic waves, this one already tells you that V is 3 times 10 power 8 meter per second. Find out the wavelength given the speed and the frequency. This one, very simple. V is F lambda. V is 3 times 10 power 8. Frequency is 3.7 times 10 power 15 times lambda. Lambda is therefore 3 times 10 power 8 divided by 3.7 divided by 10 power 15. You're going to get the wavelength as 8.1 times 10 power 8 minus 8 meter, sorry, times 10 power minus 8 meter. Okay, so round it up to 2SF, it's going to be 8.1 times 10 power 8 meter. So this one is shown. Okay, so last one. State the region of the electromagnetic spectrum to which this waves belong. Okay, this one is actually the question where you need to reproduce your EM wave spectrum. So this one, just draw those vertical lines like this. Always start with 10 power 3, then divide by 10 power 3 each time. This one will be 10 power 0, 10 power minus 3, 10 power minus 6, 10 power minus 9, 10 power minus 12. Always remember to put in 10 power minus 7 here because this one is for visible light. So last time I mentioned to you, raging Martians invade Venus using X-ray gun. raging Martians invade Venus using X-ray gun. So your frequency is 3.7 times 10 power 15 hertz. Your order of magnitude is 10 power with, sorry, this one is not the one I want, sorry. I want the wavelength. 8.1 times 10 power minus 8, because this one is in order of wavelength. Okay, wavelength is decreasing. I don't want to use frequency. I want to use wavelength, sorry. So my order of magnitude for the wavelength is 10 power minus 8. So look at where 10 power minus 8 is. It's actually going to be somewhere in between 10 power minus 7 and 10 power minus 9, which will automatically mean that it's actually ultraviolet. So the region of the EM spectrum to which the waves belong is actually supposed to be ultraviolet. Okay, so the answer is ultraviolet. Okay.